What if the greatest barrier to exploring the stars is not technology, not money, not even time, but the universe itself? For centuries, humans have dreamed of traveling between stars. From science fiction to real-world space programs, the idea of interstellar travel feels inevitable. But what if the universe has built-in rules that prevent us from ever becoming a starfaring civilization? Tonight, we explore the brutal physics that may make interstellar travel nearly impossible. Humans stepped on the moon in 1969. We sent probes beyond the solar system. The spacecraft Voyager 1 is now over 24 billion kilometers away. That sounds impressive, but here's the problem. Even after traveling for more than 45 years, Voyager 1 hasn't reached another star. The nearest star system is Proxima Centauri. Distance: 4.24 light-years. That's about 40 trillion kilometers. And Voyager 1 would need over 70,000 years to get there, according to Albert Einstein and his theory of relativity. Nothing with mass can reach the speed of light. Why? As an object moves faster, its mass increases, its energy requirement increases. To reach light speed, you would need infinite energy. Infinite energy does not exist. Even reaching 10% of light speed requires unimaginable energy. Let's put that into perspective. To accelerate a small spacecraft to 10% light speed would require energy comparable to the total annual energy output of entire nations. The universe enforces a speed limit, and it's non-negotiable. There's another cruel rule: the rocket equation. To move forward, you must throw mass backward. The faster you want to go, the more fuel you need. But here's the trap. Fuel has mass. More fuel, more weight, more fuel needed. It becomes exponential. To reach extreme speeds, your spacecraft would need to be mostly fuel. At some point, the math becomes absurd. Physics wins again. Space looks empty. It isn't. Between stars, there are hydrogen atoms, dust particles, microscopic grains. At 10% light speed, a tiny grain of dust would hit your spacecraft with the energy of a bomb. Shielding against this would require massive protection. Massive protection increases weight. Increased weight increases fuel needs. Again, physics traps us. Even if we solve energy and shielding, time becomes the next enemy. At 10% light speed, travel to Proxima Centauri equals 42 years. That's one way. Round trip? Nearly a lifetime. At slower speeds? Centuries. Options scientists discuss: generation ships, cryogenic sleep, AI robotic explorers. But human interstellar tourism? Extremely unlikely. Einstein's equations allow strange possibilities. Wormholes, shortcuts through space-time. In theory, they could allow faster than light travel, but there's a catch. They require exotic matter with negative energy density. We have never observed stable exotic matter. Even if it exists, controlling it may be impossible. So wormholes remain mathematical possibilities, not engineering plans. Some physicists suggest only extremely advanced civilizations, far beyond ours, might achieve interstellar travel. But even then, the energy requirements are staggering. To move starships at relativistic speeds might require harvesting the power output of entire stars. That's not a spaceship. That's a civilization-scale engineering project. Interstellar travel may not be impossible, but it may be so difficult, so energy-intensive, so dangerous,